So we're still talking about the energetics, and you'll see that these lattice structures end up leading into coordination environments. So what we need, see, if we really want to define the energetics in here, we need a relationship between ion radius, enthalpy of hydration, and the enthalpy of the lattice. Okay, so I gave you just a simple sodium chloride crystal here to kind of get an idea of where each one of these ions is at. And everything's going to be based off the sodium in the very center. Okay, and so we're trying to figure out the energetics of the solution. Okay, so what we're really looking at here is the internal energy of the system. No, I need my writer on. This is why I don't like when physics textbooks use U for potential, because in thermodynamics you use it for internal energy. Your total internal energy I say that, but in this case, the internal energy is actually a reflection of the potential between the ions, but I still like to make that difference. So we want to figure out the total potential, the total internal slash potential energy of this system. So we're going to start at that sodium right in the middle, and what we're going to do is that 0, 0, 0. We're going to kind of set these at coordinates. Okay, so all of your other ions with respect to that central sodium, tell me if this makes sense to you, are at so R0 is going to be the radius of the sodium right in the center. Okay. Now, what is that? What is that coefficient?
The coefficient?
Mm-hmm.
The R0? Wait.
So the R0 is the radius of your central sodium there.
Radius.
All your other ions with respect to that sodium are at a distance of x squared plus y squared plus z squared, square root of the whole thing.
Looks kind of Pythagorean theorem.
It does. It should look very similar to something we've done in physics, but we've only been doing it in 2 dimensions.
Gosh.
So if I wanted to know the position of that with respect to that central sodium, do you know what I just did there?
I mean, no, I guess I don't.
So that's a position vector.
Okay, it's just vector?
Mm-hmm. And so the x squared plus y squared plus z squared is the what?
I feel like I should know that.
So what if you just did it in 2 dimensions? So let's say, I don't know, because we're already using R for radius, so let's call this position vector. Okay, so what if I had let's change this a little bit to say what does that look like?
I mean, it just looks like a coordinate system to me. I don't know.
That's the magnitude of the position vector.
It's the magnitude of the position vector.
Mm-hmm. So you're looking at the magnitude. So you have a position vector going from the central atom to all these other atoms, and you say, well, I need the actual magnitude of that distance as a function of R, multiplied by R0 to really give me the separation of these ions.
Okay, so it's just the exact distance
Mhm.
from the. Okay.
Yeah, it's just
Okay.
we're working in a three-dimensional environment. So I wish you all took 200 level physics because we'd be doing it this way. But if you only started college a few years later, because the vice president is like, yeah, we're going to be moving that way. Eventually, our pre-meds, everybody's going to be taking calculus-based physics.
Nice.
Because the other day she goes, I'm really just kind of over the dumbing down of education. She goes, we're going to build people with real skills.
That's nice. That's good.
So,
I feel like if you can be a doctor, you can do a little bit of calculus, right? You know
yeah.
what I mean?
hmm Plus, with the pre-engineering coming in, our pre-meds and health science students are used to being the best.
Oh yeah.
Um, well, we had students like you are few and far between, so they don't really have much of a comparison.
Yeah.
But when we bring in engineering people, they're going to have a whole crop of students who are challenging them for the top position.
Oh sure. Yeah.
See, we have like you and like one other person who's like a pure science major who, it's like you blow most of them out of the water. They just don't pay attention because you're just one Sonia.
Yeah, I guess. That's
Now
true.
you're doing like a lot of intense bio and chemistry. Maybe in the future you can change it so that there's multiple Sonias.
Yeah. Get more of me in there.
Yeah. But would you want to copy yourself and deal with that?
I don't know. I like to think I'm easy to get along with, but maybe not.
Well, but that's the thing. You can be easy to get along with for another person, but are you easy to get along with for you?
Yeah, probably not. No. I'd be like, who's this nerd?
So yeah, we're working with the position of each one of these atoms, and that's the distance that they are from that central atom. Okay, so let's look at the nearest chlorides. Okay, so that's going to be these six, that six coordinate shell. And can you kind of see how that's like your octahedral?
Yeah.
Yeah, so that's your octahedral environment. So each one of those are going to be, I'll do this 3 times instead of 6, plus or minus 1, 0, 0, 0, plus or minus 1, 0. So pretty straightforward. And so for all of them, we only have to do this once. Your D, your distance from that central sodium, we'll just do the one that's in the x direction. So it'll be 1 squared or negative 1 squared. And so it's a distance of R0 from that sodium right in the middle. Okay, so let's start thinking about, let's start our internal energy by thinking about Coulombic potentials, okay? Okay, so a Coulombic potential. Now, this is going to take on a slightly different form. The most basic form in algebra-based physics is, do you remember what that is?
For what?
So a Coulombic potential.
A Coulombic potential. Is that the V? No.
Well, if you have the 1 over 4 pi epsilon 0, what comes next?
Epsilon 0. Man.
You're like, I did this weeks ago.
I did this not long enough ago. I should remember.
So this is your Q1, Q2 over R. But in our case, Now this will be over R0, but we need to think about how to put Q in here.
Okay. Is
What's a good way to calculate the Q of an ion?
you want the Z? No. The effective charge or like
No, let's make it a little more simple than that. So what we're going to be doing here is we're going to say, well, it's going to be ZE, ZE.
okay.
Make sense now?
Yeah. Okay, I see it.
And so then, of course, in this case, Z is really going to be the magnitude of your charge. So it's like for a sodium, it's a 1. Okay. Right. For a chloride, it's a 1. For a magnesium, it'd be a 2. Okay, so and then of course they're all going to be, well, I guess that'll be a negative because one of a sodium and a chloride. This is going to give us negative C squared E squared. And if we look at this environment here, what do you think the total potential is going to be? Look at that octahedral environment. So this is the potential between two ions.
Is it just gonna be like 6 times that?
Yep. Now, that is the potential for those chlorides. Now, what about the following sodiums? Okay, well, where are those? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nope, don't count the center one. 11, 12. There we go. So we can only count the I almost put the center one in its own coordination sphere. Yeah, don't do that.
Why not?
Because you're measuring everything from that center.
Okay.
You can't have something coordinated to itself. We kind of run into a problem in that in quantum chemistry with something called density functional theory, where you have to mathematically tell the program to not count an electron's interaction with itself as a repulsion.
Oh, okay.
So kind of the same idea.
Sure, okay.
You can't count the atom at the center of the coordination sphere as interacting with itself.
Okay, that makes sense.
Okay, now, so that's 12 sodiums. Now let's think about where they are. So you notice those chlorides were at nice, vertexes.
Right.
Okay, but these are going to be at combinations. So they're going to be 12 sodium ions at plus or minus 1, 1, 0. And okay, so the distance to each one of those, let's see, let's just say 1 squared plus 1 squared plus 0. So that's going to be your distance to each one of those. Now, again, this D, we only have to do it once because I think you notice if you put any combination of those in there, you're going to get the same answer.
Yeah, right.
So we don't have to do that whole thing again. We know that this potential is going to come out to be 12. This time it's square root of 2 R0, not just R0. Does that make sense how in the first one it was just R0 down there, and now it's so I think the clearer way to look at that is there. If we start our potential with D instead of R at the bottom.
Yeah.
Okay. So now you see why this one down here adjusts to square root of 2 R0.
I get it. I get it.
And so then what we have is we have 8 more chlorides at these positions. Okay, so that's going to be 8 of those. And those are going to be various combinations of those. So your D and this time we get square root of 3. R0 and a potential of 8. Don't forget the negative sign. Because we're building up to something here. So now let's kind of look at this as a total. Now you know, of course, this is just a small section of the crystal. You know that we could just keep going and going and going and going and going, but this proves the point. So our total U is going to be R6. Let's see. Plus R12. No, not that negative sign. What mistake did I make? I want you to find it.
What was it watching? What mistake did you make?
Yep. I am removing that negative sign. Why did I remove that?
Where? Which one?
So,
On the sodiums?
yep. So, yeah. I'd carried down a negative sign there. It's a good exercise.
Oh, because they're both positive.
They're both positive. So yeah, I almost got a slightly incorrect answer. They're both positive, so I don't need a negative sign there. So that means take that one out. And now we're correct. Let's see. Okay. So you know, of course, then this could go on and on and on. And so what I want to do now is pull out so I'm going to 4 pi epsilon 0 R0 negative z squared e squared, which inside the parentheses now is going to leave 6 minus 12 over square root of 2 plus 8 over square root of 3 minus so on and so forth. Okay. Now you have come across a brand new constant. which they call N. And this, when you're looking through more advanced textbooks, is called the Madelung constant. You find this constant a lot in solid state materials. It's going to be something that really helps to describe solid state materials. Okay, so let's look. So what we have here is we have two internal energies, two potentials, where our attractive potential is now going to be a variation of this, so negative and A, Madelung constant, C plus, C minus, C squared. We have that.
Is it just R, not R0?
Yeah, so this is just a generalized R. The first part we were using a specific crystal to get to this point, but now we can see that we're at, we're here, and this of course would be the attractive because we have the Z plus and the Z minus. We can't just simply call it Z squared. But you can work through the math, but our repulsive potential is going to take a format and in this case, B is the repulsion constant, and N is your Born exponent. So we end up with a U total of our attractive plus our U repulsive. And you remember that NA is, right?
Avogadro.
Yep. And of course, that R is still representing the spacing between your ions. Okay, now we start to have a little fun.
Wait, I have a question.
Mhm.
For the Madelung constant, is that like a series? Is that what that is?
Yes.
Okay. We just started talking about that in calculus.
Yeah, it's a series. And you would really run the series over any, like the sphere you want to examine.
Okay.
Now, we're going to start talking about the R0. So in this case here, we have R as a general sense. That R0 is going to be an equilibrium distance. Okay, so in any molecule, we've never seen a dissociation curve, but that would be helpful right now.
Dissociation curve.
Yeah, so like for hydrogen, you have energy on that, and then separation on that axis. You get a curve.
Oh, I saw this in the book, I think.
Yeah. And so, and each one of these is here you have hydrogen real close together. Out here, they're essentially at an infinite distance, so they're separated. Here,
It's like the optimal distance.
they're the energy minimization is where they're going to be at that R0. And so, since we know that energy is minimized at the optimal distance, okay, you're taking calculus. What does a derivative equal at? So a minimization is going to be an extrema on the graph.
So it'll be 0?
It's 0.
Heck yeah, I
The
remember
derivative
that.
is 0. So this is what we're working with. Now, we have to do the derivative of this fun thing. Cool. All right, so let's think about that. This will be a good exercise for your class. DDR. And a lot of times in more advanced textbooks, you'll see all of these represented as partial derivatives because you can do that most of the time because everything else in there is going to become a constant except for R anyway. So you could just leave it like this as the proper derivative, or you could do a partial derivative. Or you have the
Delta.
Yeah, the funny, well, they're not quite deltas.
There's funny D.
Yeah, look up the partial derivative. You'll see what I'm talking about.
I've seen people draw them, I think,
But, well, okay, so let's think about this. Let's think about this derivative. So we're going to say negative. So I almost called that 70. Hang on.
Chemistry.
Mm-hmm.
Everyone's good.
There we go. So now we have to figure this out. Okay. So the first thing you know is that derivatives distribute.
For sure.
Remember that?
Yeah.
Okay. So the derivative is going to go to this one and to this one. Okay. And we also know that it's only interested in the R values. So everything else is going to be a constant. So what we end up with I will say in physics, you're going to be getting a problem where you're going to have to do force on a magnetic force on a current carrying conductor. And the current will be going in some random direction and the magnetic field will be going in some random direction. We're going to see how people handle that. So Z plus, Z minus squared over 4 pi epsilon 0 d to dr of r to the minus 1. I like to do it this way. You could do d to dr 1 over r if that's more comfortable for you.
I write it like this every time.
But this allows me to see the exponent that I'm working with. And you can use the power rule and we get plus NAB d to dr r to the minus n. Okay, now we want to figure this out. Yep. Tell me what this derivative is.
R to the minus 1.
Mm-hmm.
Okay, it's been a while since I've done a derivative. I can't even lie.
Power rule.
Power rule. It's just gonna be 0, right? Wait, no.
Nope.
It'll be just -1. Wait.
Kind.
Because it's like
well, you get a -1 out front. So you remember your power rule.
to the -2.
Yeah.
R to
So it's
negative.
a negative r to -2.
Okay, yeah. Yeah.
So we're negative 1 over r squared.
Work.
Okay, now more generalized. All right, so we know that exponent pulls down in front, so negative n. and R minus N minus 1.
Heck yeah.
So we just use the definition of the power rule. Or negative N R. We just pulled negative 1 out front. Equals a negative N over R N plus 1. Okay, so now we have our derivatives. Now we're just going to go ahead and put these back in. And put them in there. There's substitution. And then we have negative 1 over R squared. NAB. Negative N R N plus 1. And of course, that all equals 0. Or we end up with, and we remember that this is at our equilibrium, at our minima. So that's our equilibrium distance. So we can go ahead and start substituting in our 0. So on this side, we have that. Then we have a minus. S N B over K. Now let's go ahead. Yep. You can imagine hundreds of years ago, people were very bored.
Yeah, right.
I love it when in physics class when people go, why did Isaac Newton do this? Well, it was the 1600s and it was the plague.
What else were you supposed to do?
You're not going outside. You didn't have video games or Netflix. So you either stared at the wall or you invented physics. It was
Exactly. Two options.
So, okay, so now we're going to do okay. Because I hope you notice we're solving for the repulsive constant.
The B.
Mm-hmm.
Heck yeah.
So when we do that, our first iteration of this is going to be, so you see that the Avogadro's number divides out. Okay, that's our first iteration. We need to think about how we can reduce down those R's. Okay, so we know that what does this equal?
N minus 2.
Ah,
Or N minus 1, sorry.
yeah, so I
Already
can go, that's R0. We do the N plus 1, subtract off the 2, R0 minus 1. So our B then becomes Were you into high school? Did they have good math there? Or was it kind of like your dad pushing the issue?
A little bit of both. I think I cared about math in high school.
Yeah, that's also always an option. So we end up here, okay? Now we want to round out our repulsive energy, so we remember what that is. It's that right there. Okay, so if our repulsive energy is going to be NAB over RN, because there's things that you know, like off the top of your head, but I have a hard time getting anyone else to answer.
I think I don't know. I think if I do a math skill enough times, it just sticks.
Yeah.
You just have to do it, is all it is.
Yeah, it is a lot of it's practice. I mean, that's why I'm doing in physics what I'm doing. I'm doing it to chemistry too. One of the ways that I got good at this was I just went through textbooks.
Yeah.
I worked through textbooks till I could derive every single equation, and then I moved on to the next one.
Yeah. I think also a lot of people see math and they panic and they don't really want to, like, I think it's just an immediate, I don't know how to do that, so I'm not going to try.
People try to look through the textbooks for well, why is it this way? Well, but if you work the math until you understand it,
yeah,
then you're going to see why it is the way it is.
Yeah, it makes sense. It's just like not laid out for you perfectly.
Like doing the cross product in terms of vector determinant. If you took two vectors, you crossed them together, to figure out the direction of the third vector, you can either do the arbitrary right-hand rule trying to figure out which way it's going, or you can do the cross product, and you're going to get a third vector that has very exact directional components.
Yeah.
And you're going to be able to see, oh, so if I make a base of a parallelogram out of these first two vectors I'm crossing, the third one is going to be a side of the parallelogram that's perpendicular to the first two. It's just the math actually makes it so you don't have to guess on the direction of the third vector. It's just, I find that it helps.
Yeah.
So when we substitute in our repulsive constant, if I was ever a rap star, that'd be my rap name. Names.
So can you do the whole equation?
Name zero.
Name zero.
That would be awesome. And then you could, let's go back up. You could then make a joke about something being like, call yourself like Kapustinskii at one point. And people go, wait, what?
What? Who's Kapustinskii?
Name zero.
That's me.
Trust me, nobody would want that.
No one would think it's funny. No one would think it's funny.
What I love is those little inside jokes that only a few people would get. Like every physicist would go, oh my gosh, I totally get it.
Yeah, you'd have a very niche audience.
Mm-hmm. Now look, we have another reduction to do.
Great.
So R0n minus 1 over R0n. So again, we subtract the exponents.
I can.
N minus 1 minus n equals R0 minus 1 or 1 over R0. So this is going to give us a repulsive energy now it's just names again.
Yeah.
And there's our repulsive energy. Now, of course, we remember.
Wait, am I crazy? Where did the n go? In the denominator.
It's supposed to be there.
Okay, cool.
There we go. I just missed it. Okay, now we go back to our total internal energy where that's our attractive energy plus our repulsive energy. So that first one, remember, is our negative. And so then our attractive energy and if I pull everything that's common out front, on the inside here, I'm going to get 1 minus 1 over n. And of course, that n is our Born exponent. And so we end up at the Kapustinskii equation. And so this is going to be a measure of the internal energy of that coordination environment for this material. Now, one thing that does help is, first off, Kapustinskii. So we're going to abridge this a little bit. But the Kapustinskii noted that your M is usually between 0.87 to 0.88. Nu, so you're going to getting a vibrational frequency. And R0, of course, we need to split this apart to be. So those are our ionic radii. So one thing Kapustinskii did was he made an approximation. So the 1 over n. What that's doing is it ends up giving a measure of crystal compressibility. But he ended up setting a common distance through a lot of work, a lot of experiment, but he found that this kind of common distance gets you the most accurate answers across a wide variety of materials.
So it's like a good enough approximation.
Uh-huh. And so then, we'll go back and we'll look at your n being your 0.88. And what he said is you can really approximate nu by formula units. Okay, so what you end up getting and you end up with the equation that you saw where you get a nu And this is a very accurate approximation of the enthalpy of the lattice. So all of that extra stuff, so that K is your Kapustinskii constant. Eventually I'll get that name right. And all of the things that you don't see in there are now wrapped up into that constant.
Okay.
So your 0.88, your Avogadro's number, your E squared, which is your base charge, your 1/4πε0, those are all wrapped up in the Kapustinskii constant. So this is how we end up at a relationship for internal energy of a coordinate system or a crystal system, especially when we're trying to figure out. So this is in particular the enthalpy of the lattice structure. A lot of fun math to get to something and be like,
Yeah, I like the approximations.
and so between these two equations we worked through, the Born equation and the Kapustinskii equation, we now have solid relationships between the radius of an ion and the enthalpy, the internal enthalpy of the system.
Cool. Sick.
So, oh wow, we did run out of time, didn't we?
Does this change, like, the sodium chloride has a pretty, like, normal shape. Does it change if